Hi class, in this lecture we're going to begin our study of logarithmic functions, and this lecture is going to have a lot of information. It's going to be kind of a lengthy lecture, and we're going to start by introducing what exactly is a logarithmic function, talking about a lot of their properties, graphing, and then ending on an application problem. Okay, so here's our objectives, what we're going to work through in class today, or in this lecture today. So first thing we're going to talk about is how you change from logarithmic to exponential form, and then how you change from exponential to logarithmic form. And even before that, I'll talk about what exactly is a logarithm. We'll talk about how you evaluate logarithms. Then we'll use basic logarithmic properties. Then we're going to graph some logarithmic functions. And then we're going to find the domain of a logarithmic function. We've got some great examples of that. And then we're going to talk about common logs and natural logs. So you'll hear me say the word logs a lot during the lecture instead of logarithms. It's just the short version of it. So common logs and natural logs, and then we'll actually, at the end, we'll work in application problem. Okay, so let's jump right into it. What are logs? Okay, so no horizontal line can be drawn that intersects the graph of an exponential function at more than one point. So like if you were to take an exponential function, if you remember, let's just take a very simple one. Something like this. F of x is equal to x squared, right? So we remember that it looks like this. So it passes the horizontal line test, basically, is what this first is saying. So this means that these exponential function is 1-to-1 and it has an inverse. Okay, so our goal first here, find the inverse of an exponential function. Okay, so how do we do that? How do you find the inverse of an exponential function? So if you remember from your college algebra class, you just f of x is equal to b to the x. Okay, b is the base. So you write this as y is equal to b to the x. Then you flip the x and y. And you try to solve for y. So x is equal to b to the y. So how do you solve for y here? And it's like, I don't know. I'm not sure here how to do this. And that's when we're going to need to introduce this thing called a logarithmic function. So the inverse function of an exponential function with base b is what's called the logarithmic function of base b. So the inverse function of f of x is equal to b to the x. Oop, a little bit of a typo there. b raised to the x power is this function right here, okay? I'll also just call it f of x. It's equal to the log base b of x. So this log, think of the log itself as a function, right? So like what I'm inputting into the log base b is the value x here. Okay, so this is the inverse function of b to the x. Okay, so here's the formal definition here. And then we're going to work a lot of examples with this. So this only works for x greater than 0 and b greater than 0, all right, and b cannot equal 1, okay? We have the following. Y is equal to log base b of x is equivalent to b to the y is equal to x. Okay, so this function, f of x is equal to b, log base b of x is the logarithmic function with base b. So look, let's use this here, okay, to illustrate the concepts, okay? We'll start with an exponential form, okay? So this is exponential form. All right, so let's just take b to the y is equal to x. So I don't know, let's just say something like this. 2 cubed is equal to 8. I think we can agree on that, right? And now this is the log form, logarithmic form. So it's y is equal to log base b of x. Okay, so look, what is the base here? The base is the 2. the exponent y is a 3. So it's 3 is equal to log base 2 of 8. Right? And what I'm saying here is these two are equivalent forms. They're just different ways of saying the same thing. Okay? So let's now do some examples. So we're starting to kind of get an idea of what the log function is. Okay? It's the inverse of the exponential function. Okay? And let's start, let's get some practice of switching between these logs and exponential form. Okay? So just remember this this equivalent statement here, and I'll come back to it. All right, so what I want to do here is I want to write each equation in its equivalent exponential form. So looking back, b to the y is equal to x. All right, so excuse me, I'm starting in log form. Y is equal to log base b of x. This is equivalent to, going back, b to the y is equal to x. All right, so look, our b here, okay, I want to write it in exponential form. That's this form. Our base here is 2. So it's 2, the exponent is y, so 2 to the 4 is equal to 16, and that totally makes sense, right? 2 times 2 is 4, times 8 times 2 is 8, times 2 is 16, so it works out. So here, look, b is the base. So b, y is the exponent here, so y to the 5th power is equal to 32. And you can see that b is just equal to 2 here. It has to be. All right, now I'm moving it around. Okay, I'm just flipping it a little bit. Look, the base of the log here is 5. So this is 5, okay? The exponent is y, so 5 to the y is equal to 125. And I think you can see here that y has to be 3, right? Because 5 cubed gets you 125. And then look, you can just see this one. The base of the log is the base of the exponential, right? So 9 squared, okay, that's my y. It's the exponent. 9 squared is equal to x. And you can see here that x just has to be 81. We can solve for these, right? We can see, what they equal just by looking at it. All right, so now let's go the other way. So let's take exponentials and put it into log, okay? So b to the y is equal to x is equivalent to, okay, y is equal to log base b of x. So look, the base here is 2, okay? The exponent here is 3. So this is 3 is equal to log base 2 of 8. We got it. What's the exponent here? The exponent here is 4. Okay, so this is 4 is equal to log base 5 of 625. Okay, helps to see this here, okay? What is the third root? Another way of rewriting this is 64 to the third root is equal to 4. Okay, so what's my base here? My base is 64, and my exponent is 1/3. So this is 1/3 is equal to log base 64 of 4. Exponent here is y. Y is equal to log, what is the base here? 8 of 300. So here's all I was doing. I'm just switching between exponential and logarithmic form. Just going back and forth, back and forth. They're equivalent statements, okay? All right, so now let's talk about how you're going to evaluate each of these. Okay, so I want to figure out real quickly here. This is interesting. Log base 2 of 64 is equal to what? So to do this, to evaluate these logs, what you're going to want to do is switch to exponential form. Okay, let the question mark be equal to x. and then solve. All right, so it's base 2. 2 to what power is equal to 64? Well, think about it. 2, 4, 8, 16, 32, 64. So look, x has to be equal to 6. Base is 5. 5 to what power is equal to 1/5? Well, here it has to be -1. Yeah. So this is what we're saying. Look, and I skipped a little bit going on here. So what we're saying here is log base 2 of 64 is equal to 6. And here, log base 5 of 1/5 is equal to -1. And look, you can see what's going on here. 7 squared, or I already gave it away. 7 to what power is equal to 49? Yeah, it has to be squared. So what's going on here is log base 7 of 49 is equal to 2. All right, now this one's fun, okay? What is my exponent here? So log base 7, so 7 to what power is equal to the square root of 7? Well, look, square root of 7 is the same thing as 7 to the 1/2. So what does x have to be? It has to be the same thing. It has to be 1/2. So this is what we're seeing. Log base 7 of the square root of 7 is equal to 1/2. Okay? You'll notice one thing I just want to make clear, like when I write my lectures, I always put parentheses around these to let me know that it's the log of 64. But you know, you'll notice when you look at your homeworks and you know, the e-text, they don't do that. Okay, so I just want you to know that I do that. That's just a thing that I do. Otherwise, you know, with my sloppy handwriting, sometimes things get jumbled if I don't do that. Okay. So now let's talk about some basic properties of basic logarithmic properties involving 1. Okay, so log base b of b is equal to 1. So if the base and what's being inputted into the log is the same, it's always equal to 1. Okay, because 1 is the exponent to which b must be raised to obtain b, right? So b to 1 raised to the 1 is just b. And log base b of 1 is just 0. Okay, and this is because 0 is the exponent to which b must be raised to obtain 1, right? So b to the 0 is equal to 1. All right, so remember these. These are important. When the bases are the same, it's equal to 1. And log base b of 1 is always equal to 0. Then we also have the inverse properties of logarithms. Okay, and again, b has to be greater than 0 and b cannot equal to 1. If you have log base b of b, but b is raised to the x power, okay, all right, remember, so like, you know, I hate to say it this way, but think about the bases canceling each other out. Like, not really what's going on, but you know, we'll talk about advanced rules of logs later, and this will make more sense. But this is just equal to x. And then same deal here. If you have b raised to the log base b, bases are the same, of x, that's just equal to x. Okay. So let's work some examples involving these. Okay. Just so you can see exactly what's going on. All right, so let's evaluate the following. Here's the first one. Log base 9 of 9. Well, look, bases are the same. Bases are the same. When the bases are the same, this is just equal to 1. And then here, log base 8 of 1. Well, look, log base, any base of 1 is just always equal to 0. Always equal to 0. And now let's try these. Log base 7 of 7 raised to the 8th power. Well, look, base are the same. Boom, 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 7. So what is that equal to? Well, look here, whatever the exponent is. Okay, in this case, the exponent is x. So here, the exponent is 8. So this is just equal to 8. And then here, 3 of log base 3 of 17. Well, look, let's go look at our other rules. Base b and b, they're the same. It's just whatever's inside the log, which is just x. So in this case, it's just 17. All right, so we're going to use these rules. These are important. These rules are going to come up a lot in the coming lecture. So have them handy and make sure you memorize them. All right, now let's talk about how you graph exponential and logarithmic functions. Okay, and remember they're inverses of each other. Okay, so you have to remember going back. Okay. So if I have the graph of f of x is equal to 3 raised to the x power, and I want to graph on the same rectangular coordinate system, okay, g of x, which is equal to log base 3 of x. All right, so recall, okay, these functions here, 3 to raise to the x power and g of x, log base 3 of x are inverses. So what that means is, okay, that the points here, if I have the first ordered pair, and you'll notice I already filled this out. If I wanted to graph 3 to the x, right, I'll pick the points -2, -1, 0, and 1. Okay, this is my x and y points. The flip over here are the x and y points. So if I take 1/9 here and plug this into g of x, well, that has to be -2. So they're just the corresponding flips of each other. So if I take 1/3, which is the y value over here, and plug it into g of x, that has to be, it has to be -1. Here, if I take 1, well, what does our rule tell us, right? So log base b of 1 is always 0. Which is the x value over here. And you can totally see what's happening here, right? When I take 3, g of 3, log base 3 of 3, what does our property tell us? That's 1, which is the same thing over here. So with the inverse functions, right? So if I wanted to graph log base 3 of x, I would find, I would use the exponential and then just flip the points around here. All right, so let's graph them, okay, on the same system. So f of x here, a -2. So I'm going to graph f of x first. Right? It was -2 is 1/9, and -1 is 1/3. Very, very just rough points here. It's hard to get these perfect. When I plug in 0, it's 1. When I plug in 1, it's 3. And then if I had done 2, it would have been 9. But you can see that this is roughly looks like this. And look, it has a horizontal asymptote. Okay, so f of x is equal to 3 to the x. Has a, this is important, horizontal asymptote. At y is equal to 0. Now if I do this one here, let's go back, okay? I got the value 1/9 is -2. So now I'm going to do g of x. 1/9 -2. So 1/9 is real close here. Here's -2. 1/3 -1. 1, 0 is the next point. And then finally the last point here was 3, 1. And this is what the graph of g of x is log base 3 of x looks like. Look. Oops, that was a terrible graph. And you can see here, all right, what's really interesting, this graph g of x, which is log base 3 of x, okay, has a has a vertical asymptote now. Has a vertical asymptote at x is equal to 0. And because they're inverses of each other, okay, if you remember from college algebra, they're inverses of each other. They're reflections along the line, so their graphs are reflections along the line y is equal to x, which is what you see, right? Okay, so that's really, really interesting. So it's another thing to note there. And so on the next slide here, what I have is I just have a much better graph of it for you here. Okay, so a little bit cleaner version so you can see, not with my terrible chicken scratch there. Okay. So let's go through the characteristics of logarithmic functions of the form f of x is equal to log base b of x. Okay, so the domain, so what's really interesting, all right, because they're inverses of each other, okay, the domain of the log is the range of the exponential. So the range of the exponential is 0 to infinity. So it's the same here. Okay, the domain of f of x is equal to log base b of x, consists of all positive real numbers. Okay, 0 to infinity. And the range, now the range, all right, is the domain of the exponential. And the domain of the exponential is negative infinity to infinity. Okay, so the range of f of x is equal to log base b of x, consists of all real numbers. So from negative infinity to infinity. All right, the graphs of all logarithmic functions of the form f of x is equal to log base b of x. They pass through the point 1 comma 0. So what doesn't matter what the base is. Okay, they always pass through the point 1 comma 0. Okay, this is because f of 1 of log base b of 1 here is just equal to 0. Okay, so the x-intercept here is 1. Okay, and this is important. There's no y-intercept. Okay, if b, the base is greater than 1, this function f of x is equal to log base b of x has a graph that goes up to the right and is an increasing function. So like this one, goes up to the right and is an increasing function. Now, if b is between 0 and 1, f of x is equal to log base b of x has a graph that goes down to the right and is a decreasing function. So if the base was like 1/2, it would come down like this. Okay, something like that. And finally, the graph of f of x is equal to log base b of x approaches but does not touch the y-axis. Okay, the y-axis, or x is equal to 0, as I showed when I graphed this, is a vertical asymptote. Okay, so now let's do some problems where we're talking about finding the domain. Okay, so remember, the domain is all real numbers. Okay, so let's look at this one here. So let's find the domain of f of x is equal to log base 4 of x minus 5. Okay, so when you go to find the domain, okay, so to find domain, I'm going to say the inside, and this is the inside of the log function, the inside of the log function must be greater than 0. So all you have to do, all right, to find the domain for these simple ones, okay? So just solve this. You're just going to say, okay, hey, when is this inside greater than 0? Well, when I add 5 over, x just has to be greater than 5. So the domain here goes from 5 to infinity. And look, what's really interesting is if you talk about transformations of functions, this minus 5 inside the log function shifts the graph to the right 5 spaces. So you can see this here now when you look at the graph. Okay, so we found that the domain excuse me, of f here is from 5 to infinity, and you can see here that that's just what the graph looks like. It's just it's just moved over 5 spaces, and this is the new vertical asymptote here at x is equal to 5. All right, let's do some other ones just so we could get, a little bit more practice here. Let's try this one. So let's find the domains of each of these. So f of x is equal to log base 3 of 2x minus 5. So again, all you have to do, set the inside greater than 0. So you're going to add 5 over, and then you're going to divide by 2. And x here just has to be greater than 5 halves. So the domain goes from 5 halves to infinity. Now if you look at this one, f of x is equal to 2 log base 5 of 3x plus 4 minus 5. So the 2 and the minus 5 on the outside, they're just there to throw you off. It's just, hey, look at the inside. This 3x plus 4 has to be greater than 0. So subtract the 4 over, divide by 3, and x just has to be greater than negative 4/3. And it's okay, or it's okay that this is a negative number, because long as x is greater than this, the inside is still positive. So the domain here goes from negative 4/3 to infinity. Okay. Now let's do some crazy ones, all right, where it's a little bit harder. All right. We'll come back to, we'll do some other domain ones in a second. Let me introduce two other, I got a little ahead of myself there, so my apologies. Let me introduce two other common logs, and then we'll talk about the domains of those with some harder examples. All right, so let's talk about some common logarithmics. So the logarithmic function with base 10 is called the common log function. All right, so this function, the function f of x is equal to log base 10 of x, is usually just expressed as f of x is equal to log of x. So when you see, like on your graphing calculator, when you see this log button right here, this just means log base 10. That's important to note. This is log base 10, okay? And this has the same exact properties, okay? So log of 1 is 0. Log of 10 is equal to 1. That's because this is log base 10 of 10. Log 10 of x is just x. And 10 log of x is just x. Okay, so whenever you see this, just remember it's got this 10 there. That's really all it is. It's just log base 10. And we're just going to call it log. Now there's another one, another pretty common one. Okay, the logarithmic function with base e, okay, is called the natural log function, natural logarithmic function. So the function f of x is equal to log base e of x is usually just expressed as this, ln of x. So whenever you see ln of x, that's going to be the natural log. And if you go back to your calculator, boom, you can see it right there, ln. What's really interesting, right, is like log base 10 and then right on your calculator 10 to the x. This is log base e, and then right there you see e to the x. And so all these properties hold. If you have the natural log of 1, that's equal to 0. The natural log of e is equal to 1. That's because it's log base e. The natural log of e to the x is just x. And then e natural log of x is just equal to x. All right. So let's do, before I was going to talk more about domains, but let's talk about simplifying these logs and these natural logs. So if I say simplify log of 100, would you agree that 100 is the same thing as 10 squared? Well, look. Log of 10 to the x power is just x. Well, what is my x here? It's just 2. So this is just 2. Natural log of e, remember, natural log is log base e of e. That just has to be 1. Natural log of e raised to the 13x. Well, look. Natural log of e, whatever the exponent is, it's just that. So this just becomes 13x. (10) raised to the log of the square root of x. Well, look. 10 raised to log of x is just x. Well, what do we have here? This is just whatever, think of this 10 and this log cancel. And you're just left with the square root of x. And then it's the same thing here. E raised to the natural log of 3,000. Right here. E raised to the natural log of x is just x. So here it's just 3,000. Okay. Let's now, I got ahead of myself. Now let's talk about some complicated domains. Okay. So let's find the domains for the following. Okay, f of x is equal to the natural log of x squared minus 4x minus 12. Okay, and then we're going to do f of x is equal to log, and then the inside is x minus 2 divided by x plus 5. Yeesh. All right, so again, what you have to do here is you have to figure out, when is this greater than 0? So you're going to look at when is this greater than 0. All right, so here's what you do. You set this up. You're going to first factor this, right? You should recognize that this factors into, x minus 6 times x plus 2 has to be greater than 0. And then what you do is you say, okay, what values of x would make this equal to 0, right? So if this was x minus 6 times x plus 2 is equal to 0, you would say, well, x is equal to 6 and negative 2. But remember, you want to be greater than 0. So you got to remember this from college algebra. But this is kind of a review, right? What you would do is you take a number line, okay? And you say, okay, here's negative 2, and here's 6. And what you would do, okay, is you would pick a value, a test value over here, like negative 3. And then you'd pick a test value in here, 0. And then you'd pick a test value over here, 7. That's past 6. And basically what you're going to do is you're going to take this test value and plug it in and see if you get greater than 0. So if you take negative 3 and plug it in here, right, what would you get? Negative 3 squared is 9. 4 times negative 3, right, would get me 12. So that's because that's positive, negative, negative. So, 9 and 12 is 21, minus 12. Look, it's positive. If you plug in 0, you would get negative 12, so it's negative. And then obviously if you plugged in 7 into this, you can also look in the simplified version here, the factored one, right? 7 minus 6 is 1, times 7 plus 2, boom, it's definitely positive. Boom. So the domain, okay? The domain of this would be from negative infinity to negative 2. And then union, you'd pick back up at 6 to infinity. All right, this one here you'd have to check to see when does x minus 2 over x plus 5, when is this greater than 0? So what you do is, again, your number line here. What you do is you say, okay, what value would make the numerator 0? Okay, well, that would be 2. What value would make the denominator 0? That would be negative 5. And then you literally do the same thing, right? You pick test values, negative 6, 0, and 3. And then you look, you see what happens. If I pick, negative 6 here, okay, what happens, right? That would be negative 6 minus 2 would be negative 8. Negative 6 plus 5 would be negative 1, but a negative divided by a negative, that would be a positive. If I plug 0 into this, I get negative 2 over 5. That's a negative. And then obviously if I plug 3 into this, this would be 1 over 8, which would be positive. So the domain is, where is it positive? Well, all the way from negative infinity to negative 5. And then from 2 to infinity. Okay. A little bit harder ones. Some of this you have to remember from a little bit of college algebra. Okay. All right, so let's use our graphing calculators now to sketch the graphs of the following. And I want to show you how to use your graphing calculator to do this and then talk about it. So here's the first one. F of x is equal to 2 times log of x plus 5. And then you can see in the PowerPoints here, I also have the graphs for you. But so here's the first one. 2 times log of x plus 5. So you're literally just going to hit y equals, you're going to go 2 times and then log, and then you'll notice it puts the parentheses there, x plus 5. Then you're going to close the parentheses, and then you're going to hit graph. And you'll notice here with these log functions, even looking here, right, the domain here is x is to be greater than -5. You'll notice that in your calculator it looks like it hits this and stops. That's just because your calculator doesn't do a good job of showing the vertical asymptote here. But so really you have to know that the graph kind of keeps going down like this. Similarly here, let's graph f of x is equal to negative the natural log of x minus 3. So negative the natural log of x minus 3. And you can see here, okay, it's going to, obviously the domain is x is greater than 3. It stops. It looks like it stops in your calculator right there, but remember, it's really shooting up forever. Okay, you're hitting this vertical asymptote, and the graph is really going up like this forever. All right, so just make note of that when you see that in your graphing calculator. Okay. All right, let's end now on an application problem. All right, kind of a fun one. Students in a psychology class took a final examination. As part of an experiment to see how much of the course content they remembered over time, they took equivalent form of the exams in monthly intervals thereafter. All right, it turns out the average score for the group, we'll call f of t, after t months was modeled by this function. F of t is equal to 88 minus 15 times the natural log of t plus 1, and this is between months 0 and 12. Okay? All right, and what this gave is the average score of the group, okay? So here's the first question. I'm going to rewrite this on the next slide here so we have room to work. F of t is equal to 88 minus 15 times the natural log of t plus 1. All right, so the first question says, what was the average score on the original exam? Well, that would be at month 0, right? So at monthly intervals, so month 0 would literally be when they first took it, okay? So average of original exam would be f of 0, which would be 88 minus 15 times the natural log of 0 plus 1. Well, what is the natural log of 1, right? So you got to look back, just remember here the natural log of 1 of 0. Natural log of 1 is 0. So this means this is just 88. That was the average initially. Boom, right there. And then next it just says, what was the average score at months 2, 4, 6, 8, 10, and then 12, 1 year later. So what we got to do is we got to find f of 2, f of 4, f of 6, f of 8, f of 10, and then f of 12. So basically, this is 88 minus 15 times the natural log of 2 plus 1, which is natural log of 3. This is 88 minus 15 times the natural log of 5, because it's 4 plus 1. This is 88 minus 15 times the natural log of 7. You can see the pattern here. This is going to be 88 minus 15 times the natural log of 9. This is 88 minus 15 times the natural log of 11. And then 1 year later, the average is 88 minus 15 times the natural log of 13. All right, so let's just start the process of, we're going to use our calculator, obviously, for these. So this is 88 minus 15 times the natural log of 3. Okay, so 2 months later, wow, look at this. The average score fell to, I'm going to write this as 71.5. Yeesh. All right, so let's see 4 months later. This is 88 minus the natural log of 5. Oh, 15, sorry. 88 minus 15, sorry, times the natural log of 5. A little bit of a mistake there. Now it was down to a 63.9. So, you can, what is going on here, right? So now we're at 88. So now we're at 6 months later, minus 15 times the natural log of 7. Look, it's like 58.8. Eight months later, let's see. 88 minus 15 times the natural log of 9. 55.0. So what you can see here is it looks like there's this big drop off, right? Initially, boom, boom, boom. And that it seems like it's starting to stabilize a little, okay? 88 minus 15 times the natural log of 11. Yep, 52.0. So you can see what happens. It's like students seem like they lose a lot of knowledge initially, but it seems like they've maintained even over time. Okay, let's even do the last one. So 1 year later, they got it, 49.5. Okay. So the next question says, but basically what you're seeing here is initial big drop initially, and then it's kind of like leveling off, right? Kind of leveling off. So using a graphing calculator, find the graph of f of t. Describe what the graph indicates in terms of material retained by students. So look, let's sketch this graph. So it's 88 minus 15 times the natural log of x plus 1 here. Now when you hit graph, you'll notice you don't see it, so you just have to zoom out. And you might have to keep zooming out until you get to it. And this is what the graph looks like. And it looks like there's a big drop of knowledge initially, and then it's a slower loss of knowledge. Okay. So here we have the graph from the graphing calculator. Big initial drop. Okay, in the knowledge retained. Okay, in material retained. Okay, which is what you would think, right? Like a lot of students, even myself when I was in college, right? You cram, and then it's really easy to forget this stuff. But then the loss of material starts to level off. Okay, it doesn't seem like they're losing as much. All right, class, I hope this lecture helped. It's a good introduction to logs, and we're going to keep working with logs in the coming lectures, and there'll be more and more of it. So you'll get continue to get an introduction to it, and a better understanding of the concepts as we continue.